Well, hello, welcome. I'm Mads Torgersen, and I'm the lead designer for C#, the language. You all know it, right? Or you're hanging out from the previous session? This is what's in my schedule today, so I just wanted to point out a few things. You were here at 12:30. There's the .NET overview talk, so run to that. I'm not going to get, I'm not going to blame you if you rush off a little early for that one. At 3, there's another talk back here. The biggest C# 8 feature is nullable reference types, and it's big enough that we broke it out to its own theater session, so I'm not going to talk about it here. Sorry if that's where you came for, but then come back at 3. And then at 4, we have a language lounge takeover, whatever that is, over in the language lounge right over here. If you want to do your own, if you want to play with nullable reference types yourself, come over and do that, and we'll be there, and we'll help you and discuss things and for an hour or so. So I just wanted to show that. I have no slides today because we have no time for slides. Instead, I'm just going to take some code, and I'm going to race through a bunch of C# features. It's going to be a little superficial and also a little artificial because we only have 20 minutes. But I hope you'll forgive me and just get an appetite for these and go more into depth on your own, exploring them in other venues. So I'm going to start out. So I have a very simple little application here. There's a program that runs through some objects and prints them out. There's an object model, interface, some classes, and a hierarchy. And then there's a service that will give me some of these, presumably from somewhere else in the cloud or wherever. And that's sort of the basis for this whole thing. So we're going to start with the language feature that's called default implementations and interfaces. This is a feature that's there to address the rigidity of interfaces as you evolve your code. So the problem with interfaces is once you've published them and people started implementing them, you can never change them because then people that implement them are all of a sudden broken, right? So if we go and say, oh, by the way, employees should have an ID property as well, you can see that immediately I get a red squiggle further down here saying, oh, now my class employee doesn't implement it anymore because it doesn't have an ID property. Okay? So up until now, you've been essentially prevented from evolving any interfaces that people rely on that you don't, in code that you don't directly control. So default implementations are there to help you with that. So we're saying that you can now add a default implementation to a member of an interface. Essentially say, if the people who implement the interface doesn't implement this member, here's how it should be implemented. Okay, so I can go and say that the getter here should, in fact, have some default behavior. So let's say that it takes the name, and maybe it does something with the hash code. So we could say get hash code in here, and essentially I'm calling members on this dot, implicitly inside of the interface here, and I can do that. I can reference the members just like I can inside of a class and so on. And the idea is you provide a default implementation. The error goes away on employee because even though the employee doesn't directly implement the interface or doesn't explicitly implement it, it's still implemented, just gets the default implementation. So that's a way to evolve your code. And that means we can go up here and try to write out, as I'm going through professors, I can write out their ID. So we could say something like, we would like to be able to say professor.id, but I can't actually because default implementations are explicit implementations of interface members. That means they don't show up on the class. They just show up when you're at the interface level. So I could take that employee that I have up here, which is the same thing typed as the interface, and now I can get at that ID. Okay, if I want to implement it myself, I can do so. For instance, we could go down to professor. Let's take a trip down to the professor and add an ID implementation. So we could say the professor re-implements the employee interface and actually adds, let's do it here, a more sensible ID. Let's say public string ID. Maybe it uses it still uses the name, but it also uses let's say the topic of the professor. Okay, so something like this. And now I made a better implementation of the ID. And now because I'm implicitly implementing it with a public member, I can go up here and actually get it off of the professor. The professor now has an ID. So you can do that. Okay, so that's how that feature works. There was just one thing that was annoying me down here in the way I was constructing the ID of the professor here. I'm like, I don't want the whole topic to show up in there. Maybe I just want the first 3 characters of the topic. That should be enough for disambiguation. So that now we're on to the next feature, which is range expressions. So I can essentially say, I can use an indexer here and say 0.3, or I can even leave out the 0 and say .3, and that means take the first 3 characters of this string, or the first 3 elements of this array, or of this span, and so on. So this is a new feature that I can generally use to slice, okay? I can get a slice, like a substring in this case. Or maybe, I want the first 3, and I want I also want the last 3. So then I can say topic hat3 ... end square here. So this hat3 here means indexes as counted from the end, okay? As counted from the end instead of from the beginning. So there's a little bit more here for indexing and slicing things. It's really good to use if you're doing things in combination with the span feature, for instance. It makes things really terse and nice, but also just for slicing and dicing arrays and strings and so on. This becomes a little more handy in the syntax. Okay, so that's already 2 features, and we're only 7 minutes into the talk. I could actually slow down a little. You got that? You good? Okay, still sitting in your chairs, except all of you are standing in the back. Sorry about that. Let's move on to the next topic. So what should we do? Let's look at asynchrony. So I'm saying that I'm getting these employees from a service somewhere. And of course, this is all fake in the example here. But typically when you get stuff that comes over the wire and so on, it takes a little while for it to come. There's latency. Maybe something's being computed. Sometimes you're looking at a real-time stream, like an IoT stream of a sensor output or something, that it actually really takes place over time. The values only come into existence over time. And that's not really good to work with in a synchronous way. You want to do it asynchronously, all right? And so we have async in the language for a while for that, but not really for streams of data. And so we added async streams, as we call it, as a language feature to C#. And here's how that works. I'm going to go and call an async version of get employees here, and it's going to get me an async stream. Don't worry about the red squiggle. And so what you see here is that the signature tells me that instead of returning an IEnumerable of T, or enumerable of IEmployee in this case, I'm getting an IAsync enumerable. Enumerable is a general sort of streaming type, the one that you can for each over. And I have an async sister of that here that is the IAsync enumerable. And apparently I can't just for each over that. What we sort of want is that for each element, the for each should await the next element. We're thinking about an async stream, and so for each round of the for each, there should be an await as well. And so instead of just saying for each, you have to say await for each in order to have a syntactic recognition that you're doing something asynchronous. Now I can't do that because I'm not in an async method, but I can just make main async, which is not an entirely new feature. You've been able to do that for a year or 2. And so now I'm asynchronously for eaching over a stream of asynchronous data, and I haven't run the code yet, and so we could do that now. And you can see that executing it, there's a little bit of a lag between things because that's how they're being produced by the asynchronous stream. Okay, so that's how you consume an asynchronous stream, how you consume an IAsync enumerable. How do I make one? Well, again, we already have language support for making an IEnumerable. We have what we call iterators, where we use yield return and yield break to gradually produce the elements of an enumerable. And I can also, let's actually go to the implementation of this one, and let's look at how this is created. And this is a similar kind of iterator, except it's async and it's producing async enumerables. So you can see that I have an async method here. It has async enumerable as its return type instead of enumerable, and it is able to have a weights inside because it's async, and it's able to have yield returns inside since it's an iterator. Right. So now we're combining async and iterators into one language feature that lets you do asynchronous things to obtain elements and then yield them out as you get them. Okay, and the consumer of them can then consume them asynchronously. So it all kind of clicks together. And there are many details about this feature that I'm not going to go into. I do want to say that one of the things that makes it makes async a little more complex than sync is cancellation. So typically for async methods, you have to explicitly take a cancellation token and try to observe that, so that if somebody has canceled what you're in the middle of doing, you'll say, oh, all right, I'll try to get out quick and not waste too many resources creating a result that people have decided they don't need. Similarly for async enumerable, there's a way for wiring through cancellation tokens, but I'm not going to show that today. You can go and look at the details in our excellent docs.microsoft.com documentation of this. Okay? So that was asynchrony. What else could we do that's interesting? We should go and have a look at the body of the method itself up here. Okay, so I'm using, what is this stuff here? Let's remind ourselves, I'm using pattern matching, which we introduced in C#7. So the is expression has been enhanced to not just allow a type, but to allow various patterns. Similarly, in switch expressions, the cases, instead of just having constants, they can also have patterns. Right? So this is an example of a pattern that we call a type pattern that we've had all along, or since C#7, that just says if you are of this type, then the pattern matches, and then the expression that came in gets assigned into a fresh variable of that type, so I can henceforth use it at that type. So instead of what you used to have to do, this is just a little recap here, instead of what you used to have to do, which is first check that it's a professor and then cast it to the professor, or do something as professor and then check for null after. Now you don't have to first check and then sort of extract the value at the new type. It's built into one expression now. I can just say employee is professor here, and now in the true branch of that, I have a professor variable in my hand at the right type that I know was there. The employee was a non-null thing of type professor. And I can then use that in the subsequent logic of the if here, and as well as in the body. Okay, but if I have an else, it won't show up, or it won't be accessible because it won't have been assigned on the false branch. So that's all good, but this is still a little like convoluted. It would be nice if there was if patterns were a little more expressive and you could extract these things more elegantly. And so this time around, we introduced what we call recursive patterns, and there's a couple of different kinds. One of them is what we call the property pattern. And the property pattern lets you put a little open curly, close curly here, and in that one you can apply patterns recursively to the properties and fields of the professor that you just got. Okay, if it's a professor, then let's start applying patterns to it. And for instance, instead of checking over here that the topic is computer science, we could recursively say topic colon and then computer science. Let me just copy the string so I don't type it wrong. Delete some things and put that in here. So now computer science here is a constant pattern that gets applied to the topic of the professor. So now the pattern says, if you're a professor and your topic is computer science, then this pattern applies. and then we will have that professor in our hand to use down here. And you can also apply other patterns. For instance, we could say that we could take one of these instead, or both of them, but let's just do one, and say, hey, and we could take your name and put that into the var pattern, which is a pattern that always matches and creates a new fresh variable called name, in this case, that just holds the result of that property. Okay, so var pattern just takes the expression, assigns it to a fresh variable of the type of the expression, which means that down here, because I introduced that name variable, I can just use that instead and not have to repeat myself dotting into the professor variable all the time. And of course, if I do it for all of them, then I can just delete the name up here. I don't need it anymore because I'm extracting all the information I need right in the pattern without the need for further dotting. Okay, so that's kind of elegant, and it's more like a declarative way of digging into the values that corresponds to sort of the shape of the object itself. And now, it so happens, maybe you noticed it in passing as I was looking at the professor type before. Professor is a type that has a deconstruct method. How many people here know what a deconstruct method is? That's just a few. So this is sort of a bit of an advanced thing from C#7, where we said, okay, in C#7 we have tuples, and we have deconstruction, which means that you can, when you get a tuple, instead of assigning it to a variable and dotting into it, you can immediately split it up into multiple variables and grab those. Okay, so deconstruction is for that, and it works for tuples, which are a special type in the language. But it also works for your own types if you write a deconstruct method. So all you have to do is write a method that's called deconstruct, and that has the right out parameters that you want, the things that you want to expose out of your type when it gets deconstructed. And now you can be deconstructed too. The compiler just notices methods of this shape, and it will let you use deconstruction on it. So you can now take a professor and you can deconstruct it. And as of C#8, you can do that with a recursive pattern. So let's go back up to our pattern matching here. And instead of using the property pattern, now that I know that the name and the topic, they are actually things that come out of the deconstructor, I can deconstruct my professor. Right back at your professor in deconstruction. So I can say, I can give it some parens here, and I can say, I think the name was first, so I can say var name, comma, and then computer science as a, I think I still have it in my paste buffer here. So instead of doing it per property, using the names of the properties, what happens is the pattern says you have a professor. The deconstruction part of it says, okay, call the deconstructor, yank those bits of information out. So now I have the name and the topic of the professor, and then the recursive deconstruction pattern here applies new patterns to those values that I yanked out. And if the pattern's still fulfilled, then I have whatever variables were produced here, the name and the professor, and I get into the true branch. Okay, so that's that pattern matching for you. There's one more thing that I'm not going to show here. That's a little, it would just take a little more code here. But I said that the other place that patterns can be used in C# are in switch statements. So that again, in C#7, we added that the cases of a switch statement can be patterns instead of just constants. Yeah, you're running to that talk, right? Yeah, go for it. And switch statements are a little sort of old school. There's a lot of syntax to write a switch statement. And so in C#8, we have a modernized version of the switch statement, which is a switch expression. And it lets you, in an expression instead of a statement, it lets you switch on a value and have cases in a much more terse syntax that apply patterns to that value. And when the patterns are true, there's just an expression instead of a sequence of statements that is the result of the switch expression if the pattern matched. Okay? So that, again, go look that up. But it's a way to, it doesn't really give you anything new in the language. It just gives you a much nicer syntax for the switch and combines well with the new pattern matching and so on. And that pretty much was our 20 minutes. Again, recommended to come back for the nullable stuff and to rush off to your to the .NET session. I'm sure that's the best session that's going on right now, but it might be a bit of a hike. So thank you very much. Come back later. See you soon.